And the last topic for tonight is the matched pairs. In this section, we're going to present methods for constructing confidence interval involving the mean of the differences of values from two populations. Basically, those populations consist of matched pairs. So now you don't have independent samples. Now you have matched pairs. The pairs must be matched according to some association or relationship, such as the following. So I listed some of them for you: before, after measurement. Remember that one of the examples was the weight of students, freshman students before and after. So this is the exact same group of people, but you measure their weights before and after. Another one can be IQ scores of husbands and wives. Interesting one. Measured at reported weights from a sample of subjects. Very good. Let us begin. Good experimental design. We're going to talk about experimental design later, hopefully next week. Many experiments have been conducted to test the effectiveness of drug treatments in lowering blood pressure, for example. When designing such experiments to test the effectiveness of a treatment, there are different approaches that could be taken. For example, measure the blood pressure of each subject before and after the treatment. Then analyze the before-after differences. 2. For the entire sample of subjects, find the mean blood pressure before the treatment and then find the mean after the treatment. Number 3, obtain a random sample of subjects and use randomness to separate them into one sample given the treatment and another sample given a placebo. So, what's the use of this? An advantage of using the matched pair from the first approach is that we can reduce the extraneous variation, which could easily happen with different independent samples. The strategy for designing an experiment can be generalized by the following principle. So basically, when designing an experiment or planning an observational study, using matched pairs is generally better than using two independent samples. So remember that. So on an interview, if they ask you, hey, what's the use of dependent samples, or basically matched pairs sample, is basically it's better than using independent samples, especially when designing an experiment or planning an observational study. So again, we're going to talk about experimental design, hopefully next week, to get better idea about these statistical steps. Notation for matched pairs. D is denoted as the individual difference between the two values in a single matched pair. Mu sub D is the mean value of the differences, like D for the population of all matched pairs of data. D bar is the mean value of the differences, D for the paired sample data. S sub D is the standard deviation of the differences, D for the paired sample data, and N is the number of pairs of sample data. What are the requirements? The sample data are matched pairs. The matched pairs are a simple random sample. Either or both of these conditions are met. The number of pairs of sample data is large, more than 30, or the pairs of values have differences that are from a population having a distribution that is approximately normal. Okay, so what are the steps? In order to find the critical values, we can use t-distribution table. For the degrees of freedom, we're going to use df to be n minus 1. So when we are using Python, we're going to use inverse t to calculate the z value. For the confidence interval itself, the confidence interval for matched pairs can be calculated this way. On the left-hand side, you have d bar minus e. This is your lower bound. And on the right-hand side, you have d bar plus e. So after calculating the margin of error, we do the algebra. Remember that the margin of error also follows a different formula. The critical value times S sub d divided by square root of n. And again, the degrees of freedom is going to be n minus 1. So let us go over one example. Try to feel more comfortable about this subject. Are people honest about their weight? It's a common belief that if you ask someone how much they weigh, you tend to get a number that is somewhat lower than the number that you would get by using a scale to actually weigh them. Listed below are measured and reported weights of random male subjects. So let us take a look at the data that we have measured and reported. So for example, when you go to doctor and they say, hey, how much you weigh? You answer 1, and then they look at your ID, you have another weight, and then they put you on a scale and they measure you as well. So the subjects are divided into 8 subjects. Subject 1, measured weight is 152.6. The second subject weight is measured as 149.3. The third subject weight is 174.8, and so on. And then the reported weight is, well, for the first subject, it is 150. The second subject is 148. The third subject is 170. But as you can see, there are differences between the measured weight and the reported weight. We want to construct a 90% confidence interval that estimate mu sub d, which is the mean of the differences between measured weights and reported weights of males. So from the table, if we find a difference between measured weights and reported weights, these are the differences that we get. So 152.6 minus 150 gives you 2.6. So the difference between these two numbers is 2.6. The difference between 149.3 and 148 is 1.3. Here you have the difference between 174.8 and 170, which is 4.8. So you continue this process. You calculate the measured, reported differences. So this is your new data that you're working with. You're going to use this list to find the sample statistic. So first of all, you have 1, 2, 3, 4, 5, 6, 7, and 8 values as the number of subjects. D is 1.425 and S sub D is equal to 5.18, 12, 16. So let us do the calculation. To manually find the confidence interval, we use these sample statistics. We have our measurements, and then we're going to construct our confidence intervals. The critical value is going to be 1.895. Let us calculate the margin of error first. Remember the formula for the margin of error. The margin of error is the critical value times the standard error, which is the standard deviation of this new data, divided by square root of n. So the critical value, which is 1.895, times the standard deviation of this new data, divided by square root of 8, which is 3.47, and the rest of the values. Okay, now that we have the margin of error, we're going to go to the next step. We now find the confidence interval. For the confidence interval itself, we know that the mean difference is bounded between d bar minus e and d bar plus e. Very good. So if you found the lower bound and the upper bound, these are the values that you have. So we have 90% confident that the limits of negative 2.05 and 4.90 contains the true value of the mean of the measured reported differences. In the long run, 90% of such samples will lead to confidence interval limits that actually do contain true population mean of those differences. So we see that the confidence interval basically includes 0. So your conclusion is that it's very possible that the mean of differences is equal to 0, indicating that there is no significant difference between measured weights and reported weights.